Okay, everyone, we are in the thick of mathematics now, as thick as you're ever going to get. This is analysis. This is the good stuff. So let's get on into the question that I was asking at the end of the last lesson, and that is, if you have yourself a power series, which looks like this, assuming it's centered at 0, then on the interval of convergence, that power series is a function, right? You stick in a value and you get a number out. So this thing, I can just call it f of x if I want to. And f of x is equal to that. If I wanted to write out the terms, this is where n is going from 0 to infinity. It would start like what? It would be a0 times x to the 0, which is 1, plus a1 times x, plus a2 times x squared, plus a3 times x cubed, plus a to the 4th times x to the 4th, and so on. Okay, so there's your power series. So the question is, given that this is a function on its interval of convergence, what's the derivative of it? So it would be awfully nice if the derivative is what you get by doing the same thing you would do to a polynomial. If this were a polynomial and you asked me to take the derivative of it, what would the derivative be? The constant would go to 0. a1 times x would just become a1. The 2 would come down and I'd get 2a2 times x. The 3 would come down and I'd get a 3 times this x squared. The 4 would come down, and so on. So that's what happens if I have a finite number of things. And the question is, what happens if that finite number of things turns into an infinite number of things? Does the same rule apply, or do things differ? It's really an interesting question, because what I like best about analysis, which is this whole area of mathematics where you're dealing with things going to infinity and things getting closer and closer to 0, is that as you go into hyperspace, remember the Millennium Falcon, it goes off into hyperspace and everything changes. When you go off into the world of the infinite, sometimes things change and sometimes things don't. You can't rely on your gut intuition just saying, oh, it's going to always be the same, because it isn't always. Okay? Just as a oh boy, I could give you all sorts of examples here. Let me just give you a quick one here. If you just take 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, that's going to converge where? It's going to converge to a number. Here's 1, here's 0, and so here's 1, then you do what? You subtract a half, and now you're down here, and you add a third, you're going to go up there, you subtract a fourth, you're going to go down there. You're going to end up converging to some number between 1/2 and 1. Agreed? But look what I can do. If I wanted to take this series, I wasn't planning to do this, but I'm kind of doing this off the top of my head here. If I wanted to take this series, notice that if I look at just these positive terms are going to go off to infinity. Why is that? Because they're effectively almost the harmonic series, right? It's the odd terms of the harmonic series, but in particular, since this thing goes off to infinity, this thing here is going to go off to infinity, and that's just equal to 1/3 times this. And so if this is infinite, this is going to be infinite, and this is going to be what I get by taking all the terms of the harmonic series and multiplying the bottom by 3. Here I'm just multiplying them roughly by 2 and adding 1. So the point is, these are going to add up to infinity as well. So the point is, I can add all these things up and go all the way out to, say, 5. Once I add up all the positive ones out to 5, then I can throw in the first negative one, which is going to bring me down there to 4.5. Then I add a bunch more positive ones until I get up to 5 again, and then I add the next negative one. That's going to bring me down here. Then I add up a bunch of positive ones until I get to 5 again, or over 5, and then I add the next negative one. The point is, just by rearranging these things, all I'm doing is adding them in a different order. I can make this limit, instead of going to this value, I can make it go to 5. I can make it go to any number I want. Isn't that interesting? I can make it go to any number I want if I have a conditionally convergent series like that. So that's just one example of something which, when you have an infinite number of things, it has a totally different behavior than a finite number of things. Because obviously a finite number of numbers, it doesn't matter which way you add them up, you're always going to get the same thing. But with an infinite number, you can get different, it can converge to different things. Okay? So that was a long remark, just basically to say that it's until you get the result from me or from someone, it's anyone's guess as to whether you can just take the derivative of this thing by taking the derivative of each one separately, or whether there's some other fancy rule that's involved. And the good news is that you can, okay? And we won't prove it. The proof gets into involved things in a upper level calculus course. But I'll tell you the result. The result is this, that the derivative of this thing is going to be, let me write it like this. It's the derivative of this. Okay, I haven't done anything there that's surprising. I'm just saying the derivative of this is the derivative of this. But here's where the magic comes, because I'm going to do what you do when you take the derivative of this thing. You say, oh, if this stopped right here, I'd say the derivative of this whole thing is what I get just by taking the derivative of each one separately and then adding them together. I'm going to do the same thing here. I'm going to say this is what you get by just taking the derivative of each one separately, and then once you take the derivatives, then you add them together. So this is the step right here that requires quite a bit of work, okay? But the point is it's true, okay? It's true. So that's the case, and not only is that the case, but let me just finish it off here. The radius of convergence remains the same. Okay? So whatever the radius of convergence was of this thing, the radius of convergence of this will be the same thing. Notice I'm not saying the interval of convergence, and you'll see why in a minute. But the radius of convergence stays the same. Okay? So let's play with this and see once what we can get from it. So here's an example. Here's an example. I know this. I know that here, I'll write ex, for example. X to the n going from 0 to infinity is equal to what? That's equal to 1 over 1 minus x, and that's on, I'll just write it on the interval from -1 to 1. Agreed? The radius of convergence is 1. So I'll write r equals 1 here, okay? So what happens if I take the derivative of both sides? Well, if I take the derivative, let's do this one off to the side. If I write this as, let's just do it. If I use the quotient rule on this, the quotient rule says the derivative of the top times the bottom minus the top times the derivative of the bottom. The derivative of the bottom is -1 all over the bottom squared, which is 1 minus x quantity squared. So those are going to cancel, and I'm going to end up with 1 over 1 minus x squared. So this right here will become 1 over 1 minus x quantity squared. And now, what about the derivative of this side? Well, let's go ahead and let's go over here and play with it again. Okay, so here we go. It's going to be the derivative of this thing, 0 to infinity, is going to be what you get by bringing this inside. So it's the derivative of x to the n and going from 0 to infinity. See that? Now what happens when you take the derivative? Well, you take the derivative of x to the n, and it's going to become what? N times x to the n minus 1. Agreed? And going from 0 to infinity. So there it is like that. I can go ahead and put that here if I want to. But generally, it's kind of nice to pretty it up. Okay, let's pretty it up in a couple different ways. First thing I can notice is that when n is equal to 0, this first term is going to be 0, right? 0 times this thing is 0. So I really don't have to start at 0. I can start at 1. Okay? So I can change that without making any difference. Then I can say, okay, instead of making this an n minus 1 here and an n there, let's pretty it up a little bit. The relationship between these two is that this thing is 1 unit bigger than this. So if I write this as x to the n, this is going to become an n plus 1. Agreed? This is always going to be 1 unit bigger than that. And then the key here is to say, well, what happens when n started at 1? When n started at 1, this started as a 0. So all I have to do here is just start that at a 0, and I'm all set. So this looks a little nicer than this. I start at 0. I don't have a n minus 1 there. I have an n, and so on. So that's a little nicer form. Okay, so here it is right here. N plus 1 times x to the n, n going from 0 to infinity. And the point is, that's going to be true. We've just found ourselves another whole series. We found ourselves another series, and this series converges on this interval. It converges on that interval right there. And so for any number between -1 and 1, this is equal to this. So for example, if I stuck in, let's stick in x equals 1/2. If I stick in 1/2, what's this going to tell me? It's going to tell me that what? N plus 1 times, I'm going to write it as 1 over 2 to the n. You agree that if I take 1/2 to the n, it can be written like that? In fact, I might as well just make it look like this. N plus 1 over 2 to the n. And n going from 0 to infinity. And then if I stick a 1/2 in here, what am I going to get? 1 minus 1/2 is a half. A half squared is a fourth. 1 over a fourth is equal to 4. So look at there. Isn't that interesting? We've got ourselves an interesting series there, which you let n equal 0. If n is equal to 0, what are you going to get? 1 over 1 is 1. When n is equal to 1, you're going to get 2 over 2 is 1. When n is equal to 2, you're going to get 3 over 4. Is that right? When n is equal to 3, you're going to get 3 plus 1 is 4 over 3, 2 to the third is 8. And then it's going to be 5 over 16, and so on. 6 over 32nd. Okay, go on all the way out. That adds up to 4. Okay, so kind of neat stuff. Okay, kind of neat stuff. Okay, let's do another one just to show you what can happen. Okay, let's just start with this one. That one has to start at 1. If you use the radius, if you use the ratio test on that thing and find the interval of convergence. In fact, I think we might have done this already. It goes from -1 to 1. There's your interval of convergence. See that? Because without this, it would be -1 to 1. But then notice that it accepts -1 as another place where it converges, because -1 to the n is going to be a alternating series here, and then it's going to be alternating 1, -1, 1, negative here, and you have a 1 over n that goes monotonically to 0, and so it does converge at -1. So there's the interval of convergence for that one. Let's see what happens when we take the derivative of it. Take the derivative of it, and we're going to get what? This thing right here. And this one starts from 1 to infinity, so you can bring that inside. Like that, from 1 to infinity. Then when you take the derivative of this, the n's are going to come down and cancel with this. and you're just going to get what? X to the n minus 1. Agreed? From 1 to infinity. And I could write it like that, but if I change it and push everything up 1, I can say, okay, that's the same as this. Note when this is 1, this starts at 0, so I might as well just make this 0 like that. So there you go. So so the derivative. So the point is the derivative of this thing is equal to this, which is our geometric series. And notice that our geometric series has a interval of convergence -1 to 1. See that? So key point here, notice that the radius of convergence stays the same. It's still 1, but the interval changed. We lost something. In general, a good thing to know about mathematics is that when you take the derivative of something, it generally becomes less well behaved. When you take the antiderivative or integral of something, it becomes better behaved. Okay, there's all sorts of examples where that happens. I won't get into a big detour here, but this is one example where we lost an endpoint here. See that? We lost an endpoint when we took the derivative. Okay, so want to do that one. Let's do another one, which is kind of cool. Let's take this one right here. Here's f of x, x to the n over n factorial, n going from 0 to infinity. And let's see once what happens when we take the derivative. The derivative is going to be, I'm going to just bring the derivative inside right away now, x to the n over n factorial from 0 to infinity. Take the derivative, the n's going to come down and cancel with this n down here. So do you notice we're going to get an n minus 1 factorial? Agreed? Because this n is going to come down here. You're going to get an n here, and that n will cancel with this n. And so instead of having n factorial, it's going to be an n minus 1 factorial. And then you get an x to the n minus 1 up here. And that's from... And so now let's see once what happens. We got rid of the first term because the first term was a constant, so that went away. So this is going to have to start from 1 to infinity now because we got rid of the first one. We had the first term was x to the 0, and that came down, and so anyway we're left with this. Now notice what happens. I can change this to look like this. I can, instead of starting at 1, when this starts at 1, then this is going to be x to the 0 over 0 factorial. This thing can start at 0, and I've got the very same thing here as here. Okay, so look at what happened. When I take the derivative of this thing, I end up with exactly the same thing as I started with. The other thing to notice is that f prime of 0 is equal to 1. Agreed? If you stick a 0 in here, let's check it out. Stick a 0 in here, you're going to get 0 to the you're going to have 0 to the 0 power, which is 1. 1 over 0 factorial is 1. All these other things will be 0. Any 0 to any positive power is 0. So we've got ourselves a function that satisfies these two conditions. Okay? The derivative of it at 0 is equal to 1, and the derivative of the function is always equal to the value of the function. And can you think of a function that satisfies those two rules? There's one that you should be familiar with. The derivative is equal to itself, and the derivative at 0 is equal to 1. Here's what hopefully you're thinking about. the function e to the x satisfies that. And let me make sure that you haven't all gone away here. Okay, very good. And so it turns out, we're going to prove this later on anyway, but it turns out that this thing right here is another way of writing e to the x. Isn't that interesting? Isn't that super interesting? That this thing right here is equal to e to the x. If you go on to Decimus and first graph e to the x, it's going to graph into something like that. And then you graph this thing out, which is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. This is why, by the way, when we took the first derivative, we were fine by changing it from -1 to 0, because this constant goes away. So you check that out and you'll see that that works just fine. So anyway, the point is, here's e to the x. You take this thing and go out a little ways with it and plot it, and you're going to see that what it does is, it's starting at 0, it hovers right around e to the x. And then once it jumps away, it just does all sorts of things depending on where you stop. But for a little while, it hovers right along e to the x. And the farther out you go, the farther it goes before it goes off on its own. Okay? So, so that's something we're going to talk about later. But interesting point. Okay. Next thing I want to do. Let's just play with this a little bit. If I take, it's maybe easier to see it in this form. If I take the first derivative of this function, then this goes away, and I'm just going to end up with what? a1 plus what? 2a2x plus 3a3x squared, and so on. Everyone agreed? And then if you take the second derivative, this one's going to go away. I'm going to get 2a2x plus what? 3 times 2 is going to be 6a3x plus those things keep going. Then if I take the third derivative, let's see, oops, when I take the second derivative, this one should have gone away. Okay, should get this. Now I take the third derivative, and this is a constant, so this goes away, and I end up with what? 6a3 constant plus the next one's going to be something with an x squared, and so on. Okay, I'm going to stop there because I just want to show you what happens when we take the third derivative at 0. Notice that it's equal to, I maybe should have done this one more time, but notice this 6 I got by taking 3 times 2 times 1. And the next one there, I would take the derivatives coming down from the power would be a 4 times 3 times 2 times 1. And next one 5 times 4 times 3, and so on. So the point is, this thing right here, I can write it as 3 factorial times a to the third, which means that a to the third is equal to the third derivative of this function divided by 3 factorial. So that tells us something pretty important. Okay? That tells us that when you have a power series like this, which ends up being a function, that those constants aren't just any old constants. Those constants are what you get by taking the nth derivative of this function at 0, dividing it by n factorial, and then times x to the n. Okay? So in other words, what it's telling you is that if you have two different power series that each give you the same function, if you have two different power series that each give you the same function, here's a to the n, x to the n, and here's another power series, b to the n, x to the n, and say they both converge to this function here. We'll call it f of x, whatever that function is. It's telling you that the only way that can happen is for these constants to be exactly the same. Just like a polynomial. Polynomial is the same thing, right? If you have two polynomials that act exactly the same way, those two polynomials, the coefficients in front of the powers of x have to be exactly the same. Same thing is true here. And why is that? Because each one of these things is just the nth derivative of this function divided by n factorial. Okay, so we will be looking at that more as we go. All sorts of good stuff here. Okay, so now we have taken the derivative. Let's go in the other direction. What happens if we take the integral, take the antiderivative? As you might expect, we get pretty much the same kind of result. And here's what it is. I'll write it as another theorem. It says that the antiderivative of a power series if you want to find the antiderivative of that thing, all you do is you do the same thing as here. You just take the antiderivative of each one separately and add them together. So I can bring this inside like that. Okay? So I can bring it inside like that. You can interchange the order, okay? And so that's one of the things you spend a lot of time on in upper level analysis classes, is proving and showing when you can interchange orders of things that are going off to infinity. This is going to infinity. This is too, because that's a limit as the number of intervals of your if you think of it as finding the area underneath something, it's the number of intervals that's going to infinity, or it's as the size of the interval goes to 0. Okay, so you're interchanging of limits is what it's called. Okay, now this, all sorts of neat things come from this. Let me show you one here. Okay, let's go back to our friend the geometric series again. Okay, so we know that. And we're going to, this goes from 0 to infinity. So we're going to integrate both sides. Okay, like so. And that's going to have the same radius of convergence. Okay, now I'm trying to remember how this all works again. Oh, you know what? Before we do that, we're going to do this. Okay, hold on just a second. I caught myself just in time. Here's what we're going to do. We're going to play with this thing. I need to watch my notes here. The first thing we're going to do is we're going to let t be equal to negative x. Okay, so we're just going to change the way things look here. If we do that, what do we get? What do we get? So x is going to be negative t. So x is going to be a negative t. So it's going to be like a negative t to the nth power, going from 0 to infinity. And negative x is equal to t, so that's going to be the same as 1 over 1 plus t. See that? And that's going to be, for x, which is going to be a negative t, it's going to be a negative t is less than 1 in size. But if you have an absolute value over this, that's the same as the absolute value of the negative 1 times the absolute value of t. And the absolute value of negative 1 is just 1. So this is just the same as absolute value of t is less than 1. Okay, so we've got that. Now we are going to integrate both sides. So I'm going to go 1 over 1 plus t dt from 0 And again, sorry about this. I'm just watching my notes here. From 0 to x is going to be equal to the integral of this thing. Oops, the summation. Okay, like that. Well, where does that get us? Won't go through all the steps of this, but you'll hopefully remember that the antiderivative of this is the ln. It's going to be the ln of 1 plus t. Let's just do it here, and then I'll erase it. It's going to be the ln of 1 plus t, and then we're going to evaluate from 0 to x. When you stick an x in there, the t just becomes an x. When you stick a 0 in there, you're going to get the ln of 1. The ln of 1 is 0. So by the time you do all of this, you're just going to get the ln of 1 plus x on this side. And on this side, we can first of all bring the tell you what, hold on just a second. Okay, had to just think through things just a little bit. Okay, here we go. And so on this one here, what happens? I can bring the integral inside, and it looks like this. And I'm going to do two steps in one. I'm going to take this thing and write it as -1 to the n times t to the n dt. See that? I can do that. So I did two things. I interchanged the order of the integration and the summation, and also I wrote this as -t to the n. I wrote it as -1 to the n times t to the n, because I can combine those again. And the reason I wanted to do that is once I do that, notice that this thing here is a constant with respect to the integral. So I can actually bring that out here and get rid of it in here. Okay, so I have that right there. And that just becomes the t to the n dt. And now what happens to that? Summation, -1 to the n. Antiderivative of this is going to be t to the n plus 1 all over n plus 1. That's the antiderivative. This is all evaluated from 0 to x, same as this one was, 0 to x. When you stick in an x here, what are you going to get? -1 to the n, going to be x to the n plus 1 all over n plus 1. Okay, and going from 0 to infinity. So we've got ourselves another interesting new series that converges to the ln. Okay, now something very important again. Everything I'm telling you today is very important. First thing is that what we're guaranteed up here is that the power series for this thing is going to have the same radius of convergence as the original. Here's the original. Once you integrate it, you're going to get the same radius of convergence. So in this case, the radius of convergence of this was x being less than 1 in size. And so what we know is, we know that the ln of 1 plus x is going to be equal to this whole series, -1 to the n times x to the n plus 1 all over n plus 1, n going from 0 to infinity. Okay? Or, if I want to make things look a little nicer, notice that I can do this. First of all, instead of having this be n plus 1 and this starting at 0, I can just make this n and make this n. And so now this thing would have to start at 1, right? Because when this thing was 0, this was started at 1 and 1. And by starting this at 1 and making an x to the n over n, I get the same thing. That's one thing I have to do. But the other thing is I have to make this thing 1 less than this, right? This was n plus 1 and this is n. So I have to make it 1 less for it. Or, in this case, since it's just negative 1 to the n minus 1 is the same as negative 1 to the n plus 1, right? Because this is just, if you take negative 1 times negative 1 squared, which is just 1, you're going to get negative 1 to the n plus 1. So I can write this as n plus 1 right there, okay? So I have all that, okay? So that is true. That's going to be true for all these values of x. For all these values of x, this series right here is going to converge to the ln function. Isn't that interesting? Okay, kind of cool. Not only that, but look at this. Look at this. Here's what this theorem guarantees us. It guarantees us it's going to work for all those. But here's what we also notice. This thing here also converges for x equal 1. See that? If you stick x equal 1 in here, you're going to get 1 to the n, which is just 1. So this whole thing here is just going to be 1 over n. This thing is going to alternate. So you have an alternating series here. So it's going to converge. So this thing converges at 1. The question is, does it converge to the right thing? All we're told here is that this is going to converge to the right thing as long as x is less than 1. But we say, hey, this thing also converges at 1. Does it converge to this thing evaluated at 1? And the answer is yes. As long as this thing is continuous, this function is continuous, which it is at 1, this is going to converge to the right thing. So in other words, here's what we have. We have at negative 1 to the n plus 1 all times 1 over n is going to converge to the ln of 1 plus 1 is going to converge to the ln of 2. Isn't that interesting? So I've had this on the board. I've had it on the board quite a bit already this semester. This is what? 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 and so on. Not only does that thing converge, but now we know what it converges to. It actually converges to the ln of 2. Okay, that's called Abel's theorem. Abel's theorem is the one that tells us that if this thing does converge at the end point, and if this thing is continuous at that same point, then it converges to the right thing. It converges to the value of this function at that end point. Okay? So, okay, there you go. I want to do one more like this, which is even maybe more interesting. So I'm going to stop. Let's see. Gonna stick with this, and now going to let's see. I'll flip my page here. And I'm going to, oh, I should have gone one more step. So one more step, this is what I had. I had that the 1 over 1 plus x is equal to, let's see, hold on just a second again. Okay, I decided it was going to be easier if I did it first and then explained it after. I don't have to turn my back to you quite so much. Okay, so here we go again. So here's our theorem. We start off with a geometric series. It's equal to this for x less than 1 in size. We're going to first just let t be negative x. So I just change every x to a negative t, and I'm going to get a negative t to the n here. I'm going to get 1 over 1 plus t in here. And that's for negative t being less than 1, but you can get rid of the negative. You can bring that outside the absolute value, and you just get t is less than 1. So it doesn't alter that at all. Okay, now I'm just going to change this whole thing right here back into x's, okay? That's going to be convenient for me, so that's all a dummy variable, so I'm going to just change it to look like this instead, okay, from 0 to infinity. Okay, so there it is. And now what? I'm going to break this up and write it as -1 to the n times x to the n, and that's all equal to this. Okay, now here's what I'm going to do. I'm going to let this x be equal to t squared. Okay, I'm just changing it into a t squared. How's that going to change things? Well, let's see. I'm going to get -1 to the n. This x becomes a t squared. T squared to the n becomes t to the 2n. And I'm going to get 1 over 1 plus t squared. And that's going to be for t squared being less than 1 in size. But t squared is the same as t times t. And for that to be less than 1 in size, t has to be less than 1 in size. So it's the same interval of interval of convergence again. Okay? Now we're going to integrate both of these things from 0 to x. Okay? So we do this one and this one. What's the antiderivative of this thing? Does that look familiar? The antiderivative of that is the arctangent of t. So it's the arctangent of t from 0 to x. That's all good. Here, when I interchange the order, I can bring the integral in. When I bring the integral in, notice that I can bring this constant outside of the integral sign, and so that comes out there, -1 to the n, and I'm still integrating the t to the 2n. So I've got that. Now I go ahead and integrate it. What's the antiderivative? You add 1 and divide by it. So you add 1 and divide by it. You're going to get that, and that's all equal to, if I stick an x in here, I'm just going to get arctangent of x. The arctangent of 0 is 0. So I get that. Almost done. Now I just stick in the x here for t and also the 0. When you stick in the x, you get this thing right here. So this whole series here is another series that converges to the arctangent of x as long as x is less than 1 in size. That's what we're guaranteed from this theorem. But notice that this is another case where this thing converges at x equals 1. See that? Because at x equals 1, you're just going to get a 1 up there all the time. This thing is going to alternate, and here you have something that just keeps getting smaller and smaller, 2n plus 1. So that's a 2n plus 1 there. Okay, so that's the alternating series test. Tells us that this thing converges at the endpoint. So I can use Abel's theorem now. Again, Abel's theorem says if this thing does happen to converge at the endpoint of the interval, of the interval that you get up here, of the interval, and if this function is continuous there, then it converges to the right thing. So in other words, if I stick in a 1 here, I replace the x by a 1, and here I take the arctangent of 1. What's the arctangent of 1? It's the angle whose tangent is 1, which is pi over 4. So pi over 4 is equal to this series, which means that if I multiply everything by 4, I get pi is equal to 4 times the quantity. When this starts at n equal 0. Yeah, n equals 0. So when n is equal to 0, you start off with a 1 there. It's going to be 1 over 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11, and so on. It's, I think, one of the most remarkable results in all of mathematics. Here you have this crazy number pi, which shows up, on a circle. And there's no way that you can write it as a rational number. There's no way you can write it as a root of a polynomial. It's called a transcendental number. It's as far away from a simple integer as you're ever going to get. Okay? And yet, we can get this thing just by taking these simple integers, the odd ones, and taking the reciprocals and flipping them alternating positive, negative, and so on. And when you add them all together, it converges to pi. Just mystical, okay? There's something just mystical there that happens. And And so that's kind of a not philosophical, but it's mystical. The other thing is practical, and that is, how does your calculator even, how can you calculate pi? When you go to a source and find out that pi is equal to, and it carries it out to 300 places, how do they get that? They don't get that by drawing a huge circle out in the snow someplace, you know, and measuring really accurately. They have to have some numerical way of doing it. And this is the kind of thing they do. This is going to converge to pi very slowly, so there's some other things that converge much quicker than this, but this is the idea. You can, in theory, you can go out as far as you want, and you can get as good of an approximation to pi as you're ever going to want with something like this, because all you can do on a computer is to add and subtract numbers and divide, multiplying, and so that's all you're doing here. Okay, so a lot of cool stuff here. So this, as I say, this is deep into mathematics here. Series and sequences, that things that are both have a theoretical fun to them. They're fascinating. You get into the infinite, which is fascinating, and then you get these kinds of results here, which just come out of the blue, which are fascinating. So very good. So that's power series. We're going to get into something just as cool next time called Taylor series coming up.